pleasure and privilege of working with a number of our best athletes, not least the young lady on the screen before you, Paula Radcliffe. And as I go through my talk today and talk about the physiological determinants of endurance running performance and how we can go about measuring those things and using the data to inform training practices, so we give the information to the coaches and you guys can apply it to the athletes that you coach. I intend to use data from Paula Radcliffe, which I've collected over a fairly substantial period of time to help illustrate the points that I'd like to make. So I'm going to start with a model of endurance exercise performance. And for endurance, it's relatively simple. And essentially, the athlete that can sustain the highest average race pace is the one who'll win. So we need to break down exactly what it is that determines that. And because endurance is aerobic, relies very much upon oxidative metabolism to supply the required energy, then it's going to be essential that we're able to operate at a high rate of aerobic energy expenditure. In other words, to operate at a high VO2, oxygen uptake. The rate of aerobic energy expenditure during any given race will of course depend upon the VO2 max, because this sets the ceiling. You simply can't operate at a VO2 that's higher than this. So we essentially often like to look for a high VO2 max in our endurance athletes. However, the actual VO2 that you can sustain for a given distance will also depend upon this, the fractional utilisation of your VO2 max. And this in turn depends upon various lactate-related parameters, something I'll come on to speak a little bit more about, lactate threshold, lactate turn point, and so forth. However, what's also important is not just the VO2 that you operate at, but how you can translate or transfer that VO2 into speed over the ground. And that's where this factor here, this parameter of running economy, becomes especially important. Of course, especially for shorter events, then there's likely to be an anaerobic energy contribution to exercise performance as well. And the magnitude of that will in part be determined by something called your VO2 kinetics. In other words, when the gun fires at the beginning of the race, how quickly can you switch on your oxidative energy system? How quickly can you accelerate oxygen uptake towards the steady state? So you'll see that all this is really to do with oxygen transport to tissue and its utilisation. VO2 will come up a lot. VO2 max, so the highest amount of oxygen you can consume per minute, what fraction of that VO2 max you can sustain, how economically you can use that VO2 and convert it into speed, and how quickly you can turn on your aerobic metabolism when exercise begins. This model was developed by Ed Coyle, perhaps a cycler, but I want to pay tribute to Jack Daniels, who's another speaker at this conference, because he was one of the first to show us that it really isn't just about VO2 max, it's also very much about running economy and how these two things interact to determine the speed that you can sustain over a given distance. Of course, the physiological determinants of performance will vary according to the distance over which you're competing. So for 800 metres, this is run at supramaximal intensities, maybe 110, 115% of VO2 max, so there's much larger anaerobic contribution than in any of the other so-called endurance events. And so maximal parameters such as the VO2 max are going to be pretty important, as is the ability to supply energy anaerobically. Whereas submaximal factors such as running economy, at least as we're about to define it, and lactate threshold are relatively less important. As we go up through the distances, you can see that the relative proportional contribution of those factors to performance changes somewhat, until by the time we get to the marathon, it's the submaximal factors such as running economy and lactate threshold which will dominate at the expense of things like VO2 max. That doesn't mean to say that VO2 max isn't important for the entire range of distance running events, just that the relative importance of these different things will vary according to the event that you specialise at. So I'm just going to review some of these parameters. I know that some of you in the audience are very au fait with exercise physiology. Others of you may not be, and so I didn't want to sort of leave you behind, so we're going to start off really at the beginning. And maximal oxygen uptake, or VO2 max, is defined as the maximal rate at which ATP, which is the energy substance in the cells that we split in order to generate energy to fuel muscle contraction, can be resynthesized aerobically. So ATP is broken down initially, and then we need to resynthesize it if muscle contraction is to continue during long-term exercise, such as endurance events, then the best way to do that is aerobically. And so VO2 max is the maximal rate at which we can accomplish that. We know from lots of studies over many years that there are strong correlations between VO2 max and endurance performance. And that's especially true in heterogeneous groups. So if you were able to measure the VO2 max of every competitor in the London Marathon, there'd be an almost perfect correlation with the highest values being recorded by the runners at the front of the field and the lowest at the back. When we look at groups of endurance athletes, however, really high-level endurance athletes, then the relationship isn't quite so strong. They all have a high value, but when they're all over 70 to 75 mils per kilogram per minute, then other factors start to become increasingly important in differentiating the performance differences between those individuals. And we know that the elite runners tend to have very high VO2 max values. So in men, 70 to 85 mils of oxygen per kilogram of body mass per minute is fairly typical, and in women it's 60 to 75 mils per kilogram per minute. And there are sex differences because of differences in hemoglobin concentration and heart size and body composition and such like. I mentioned the correlation between VO2 max and performance, and here's a reproduction of a figure from Carlson and Saltine in 1971, and it shows the best time in a group of athletes for 30 kilometres, that's approximately 18.5 miles, this was a cross-country race, plotted against VO2 max, and you can see that the runners that had the fastest time for the distance also had the highest VO2 max values, clustered around 75 mils per kilogram per minute mark, whereas those with the slowest times for 30 kilometres had the lowest VO2 max values. One thing that's quite interesting, if you look at these three individuals here, they've got essentially the same VO2 max value, around 74 mils per kilogram per minute, and yet their time to complete the 18 kilometres is really quite different. So that suggests that VO2 max alone isn't going to give you all the answers, and that we need to be measuring other factors as well, because they're clearly important. Okay, so I've mentioned running economy, so let's just make sure we're all on the same page with that. What we mean by running economy is the oxygen cost of running at submaximal running speeds. And we can have that in units of mils of oxygen per kilogram per minute, or we can convert it into the amount of oxygen it costs you to cover a given distance, such as 1 kilometre. So mils of oxygen consumed per kilogram of your body mass per kilometre of distance covered. We find with running economy that there's really significant inter-individual variability. In cycling, the differences are much less pronounced. So if we have a group of cyclists all going at, say, 200 watts on a cycloergometer, then the oxygen uptake that we would measure is really quite similar. It wouldn't differ by more than a few percent. But in runners running at the same speed on a treadmill or outdoors, we can see really quite significant differences, 10 to or even 20% differences in the oxygen and therefore the energy cost of running. There's all sorts of different factors which influence running economy, including anthropometry and body composition, some physiological factors, biomechanical and technical factors, and that's one of the reasons why the variability is so much larger in running than it is in cycling. We don't have time to delve into exactly what contributes to each of those differences, but maybe we could do that over a glass of wine later on. We tend to find that running economy is better in longer distance specialists. Whether that's genetic, so that the people with the best economy gravitate naturally towards the longer distances, or whether training for those longer distances is what actually confers the improved running economy is not quite clear. Probably a combination of both of those things. So I mentioned the variability that you can see, and here's a group of 10 runners, all running at 16 kilometres per hour on a treadmill. And you can see we've measured the oxygen uptake here. This is the oxygen cost essentially of running at this speed, which was a steady speed for each of these runners, 6-minute mile pace. And you can see very big differences in the amount of energy it's costing them. So runner 7, I think, is the least economical. He's using around 57 mils per kilogram per minute of oxygen. And runner 4 is the most economical, and he's only using about 47 mils per kilogram per minute. Incidentally, runner 4 was me, and these data were collected during my PhD around 20 years ago now. But the reason I got into exercise physiology, and particularly the physiology of distance running, is because I used to be a bit of a runner myself, and hence that's what fueled my interest in the physiological determinants of performance.